For the last module in chapter 14, I'm going to go ahead and pull all this together. We're going to learn a few more things. We're going to talk about how we determine the molar mass of an unknown solute based on a colligative property. We're also going to talk about how electrolytes will affect these colligative properties. Remember, colligative properties are dependent upon the number of particles we have. Electrolytes are things that will break apart in solution, such as sodium chloride. Sodium chloride in solution becomes sodium ions and chloride ions. So instead of one particle, it becomes two. And we're going to see how that affects our colligative properties. You also need to know the definition of the Van 't Hoff factor, which is that little letter I in the equations, and be able to calculate both the expected and observed values of the Van 't Hoff factor for a given solution. At the end of this, I'm going to work a series of problems, so I'm just going to wrap them all into this last module. So it'll be kind of a long one, but again, I'm going to work a bunch of different examples to help you get more comfortable with the concepts as well. And by that, I mean concepts from the entire chapter, not just this module. So using colligative properties to determine the molar mass of an unknown solute. There's 4 steps you're going to follow if you're trying to find the molar mass. Step 1, determine the magnitude of the colligative effect. Am I looking at vapor pressure lowering? Am I looking at a change in boiling point? Specifically boiling point elevation? Am I looking at the change in freezing point? Specifically freezing point depression? Or am I measuring the osmotic pressure of the system? Once I know which colligative property I'm looking at, I need to use the corresponding equation. So vapor pressure, we look at the pressure, the actual pressure being exhibited based on that system. Change in boiling point or boiling point elevation, change in freezing point for freezing point depression, and osmotic pressure. You do need to know these equations. Again, this is very similar to when we learned partial pressures in the gas laws chapter in first semester Gen Chem. Freezing point, change in freezing point and change in boiling point are very similar in their calculations. They are both a K factor. This is a constant specific to that material. So you should know the KB and KF values for water. Outside of that, I will give you those values. Lowercase m is molality. Remember, when we're dealing with a system that's temperature dependent, we're going to use molality instead because we don't want the temperature to affect our answer. Molar mass is a property that is intrinsic to the material. It has a specific molar mass. It will always weigh the same for that many particles. For 1 mole, for 6.022 times 10 to the 23rd particles or species of that substance, it will weigh the same amount. So molar mass is intrinsic. We need to be able to have a property here that we can measure that is not affected by temperature, and molarity is affected by temperature. And then I, our Van 't Hoff factor, which deals with the number of electrolytes we have. Or, of course, osmotic pressure, and I don't know why it's missing. There should be a little I here as well. But osmotic pressure, this is basically your ideal gas law that's just been reformed, but then at the end we multiply that by I for the number of particles we have in solution. So if it's an electrolyte, that number could be 1 or greater. If it is a non-electrolyte, that number will always be 1, but we will talk about that again in this module. Once you know which equation to use, you're going to use the definition of concentration term to determine the number of moles of solute you have. So remember molality, moles of solute to mass of solvent in kilograms. Molarity, moles of solute to liters of solution. And then just use your definition of molar mass. We know molar mass is equal to the grams of your solute divided by the moles of solute, or grams per mole. Let's go ahead and work an example. A solution of an unknown, non-volatile, non-electrolyte. Non-volatile, non-electrolyte. That is important. Was prepared by dissolving 0.250 grams of an unknown in 40 grams of CCl4, carbon tetrachloride. So I've got 2.25 grams of some unknown solute dissolved in 40 grams of carbon tetrachloride. The new boiling point was 76.97 degrees C. What's the molar mass of the unknown solute? And I'm told that Kb for carbon tetrachloride is 5.02 degrees C per molal, and the boiling point for carbon tetrachloride is 76.60 degrees C. First thing I want to do is, I'm dealing with boiling point here, so I must be using delta TB equals Kb times M times I. Because this is a non-electrolyte, I equals 1. Kb is given to me. Kb is 5.02 degrees C per mol. And I'm given the normal boiling point, Tb for carbon tetrachloride. I'm also given the new boiling point. First thing I need to do is figure out what is the change in boiling point. So I know this, trying to find molar mass. I have the information already to find this. So number 1, what is my change in boiling point? The new boiling point of the solution, 76.97 degrees C. The boiling point of pure carbon tetrachloride, 76.60 degrees C. This is a difference of 0.37 degrees C. I do have 2 sig figs here. Because I'm doing subtraction, I have to follow the number of decimal places. Now, I also have this piece of information. I'm going to rearrange this equation and solve for molality. So step number 1 is complete. Step number 2, my molality, lowercase m, is equal to my change in the boiling point temperature times that constant Kb times I. I just figured out my change in temperature is 0.37 degrees C, and the question tells me that Kb is 5.02 degrees C per mol, and I'm telling you that I is equal to 1 for all non-electrolytes. That gives me canceling out my degrees C, and this molal is in the denominator of a denominator, which actually brings it to the numerator. This comes out, and I get 0.0737 molal. Now I have molality, but how does that help me? I really want molar mass. Well, I'm told that I have 40 grams of carbon tetrachloride. Carbon tetrachloride is my solvent. This is my solute. These words are so similar. And this is my solvent. I know molality is moles of solute divided by kilograms of solvent. I know the grams of solvent. I can quickly use that to find the kilograms of solvent. With the molality, I can solve for the number of moles of solute. So step 3, number of moles of unknown solute. I've got 0.0737 moles of solute to 1 kilogram of solvent, but I'm told I used 40 grams of solvent. So 0.0400 kilograms of my solvent. This shows me that in this system specifically, I have 0.002948 moles of solute. Now, I did forget to underline my sig figs. So here I should have 2 sig figs, but I'm not going to round because I don't want to create round off error. Which means my sig figs are here and here. I now know my moles of solute. The question told me how many grams of solute I have, so I can quickly determine the molar mass. Got 0.250 grams of solute, 0.002948 moles of solute, and I calculate this out to be 85 grams per mole. Because again, my sig figs were here under the 9. Now, the math process is fine. You need to know how to do the math process, but I also want you to understand, what does this mean? What I did was I took 0.25 grams of an unknown solute. I added it to 40 grams of carbon tetrachloride. I then measured the boiling point of that system. That 0.25 grams of unknown solute caused the boiling point to raise by 0.37 degrees. That 0.25 grams was the equivalent of 0.002948 moles or 0.0029 moles of solute. That's what caused that difference. So all the math I'm undoing here, figuring out my temperature increase from it, using that to figure out my molality of my solution, calculating back to my original molar mass, all of that is based on the fact that I used 0.25 grams of this unknown. If I used a different amount of my unknown solute, I would get back to the same original molar mass, yes, but if, say, I doubled the amount of grams of solute I had, I would see a different change in temperature. So I want you to think through this process, and does this process make sense to you? Not only mathematically, but conceptually. Do you understand that if I added 0.25 grams of this to the system, it increases the temperature by this amount because it's that many particles in solution causing that the needed extra energy to reach the boiling point, because again, boiling point is when vapor pressure of the system equals external pressure, atmospheric pressure. Colligative properties of electrolyte solutions. Everything I've done so far has been a non-electrolyte. You do need to be comfortable with electrolytes. We covered these in Gen Chem 1, so if you're not comfortable with electrolytes, please review your solubility rules, and please make sure you're comfortable with that right away. But colligative properties, properties of solutions that depend on the number of solute particles, not their identity. Strong electrolytes are called strong because they completely 100% dissociate into ions in aqueous solution. Up until now, we've only focused on colligative properties of non-electrolyte solutions. But for electrolyte solutions, we have to take into account the total number of particles in the solution. So for example, NaCl breaks apart into Na plus and Cl minus. One NaCl forms two different ions. If I had 1 mole of NaCl, I have 2 moles of product. If I look at ammonium phosphate, this breaks up into 3 moles of ammonium and 1 mole of phosphate. 1 mole of ammonium phosphate gives me 4 moles of product. Because again, I don't care what the product is. It's the fact that I have more particles there that are interrupting the structures. Again, if you're not comfortable with your strong electrolytes and your solubility rules, we covered that back in chapter 1 under module 5. So let's go ahead and work some examples. The freezing point of 1 molal of glucose, a non-volatile electrolyte. So if I'm told the kf of water is 1.86 degrees C per molal, can you determine this? I want freezing point. I know that delta Tf is equal to Kf times M times I. For all non-electrolytes, if you see the word non-electrolyte, I equals 1. No exceptions. I equals 1 because 1 mole of glucose gives me 1 mole of product. It doesn't break apart. I'm told the Kf value of water. You should just remember that value. It is something that you will be responsible for. So delta Tf is equal to 1.86 degrees C per molal times the molality of the solution times 1. What's the molality? Well, in this one, it actually tells me the molality. I don't even have to calculate it. It tells me it's 1.00 molal. So I have 1.86 times 1 times 1. The calculator tells me 1.86. Let's check our units here. The molals cancel out, and I'm given degrees C. Does this mean that the freezing point of glucose is 1.86 degrees C? No, that is not correct. We're not done yet. This is the change in temperature. Water freezes at 0 degrees C. This is how much more it will depress, because it's a freezing point depression, compared to the system itself. So I need to subtract this number from water, and I get the final freezing point to be negative 1.86 degrees C. Don't forget that step, please. That step is vital. Do not tell me it's 1.86. That is not correct. It is negative 1.86 because the freezing point will be depressed. The freezing point of a 1 mol sodium chloride solution, assuming complete dissociation. So again, NaCl breaks apart into Na plus ions and Cl minus ions. That means it forms 2 moles, and we count the number of particles. I have 1 particle and 2 particle. I is equal to 2. I want to know the freezing point, so delta Tf equal to Kf times m times I. Kf, 1.86 degrees C per mol, tells me I have a 1 mol solution, and I is equal to 2. This gives me an overall answer of 3.72 degrees C, but again, that is not the freezing point. That is the change in freezing point. I know water freezes at 0.00 degrees C, so I subtract 3.72 degrees C because it's freezing point depression. If it was boiling point, I would add that, and I get negative 3.72 degrees C as the final temperature. And that is the freezing point of the system. And C, the freezing point of a 1 mol magnesium chloride solution, assuming complete dissociation. Magnesium chloride breaks apart into magnesium ions and 2 moles of chloride ions. Therefore, I is equal to 3. I know my Kf value is 1.86 degrees C per mol. I know this is a 1 mol solution, and I know I equals 3. Therefore, the change in temperature is 5.58 degrees C. So the freezing point of this solution will be negative 5.58 degrees C. So you can see from these examples that I used a non-electrolyte. I used sodium chloride, which is a strong electrolyte but breaks up into 2 separate pieces. And I used magnesium chloride, also a strong electrolyte, breaking up into 3 pieces. And each one has a different final freezing point. Assuming complete dissociation, which of the aqueous solutions below is expected to have the highest boiling point? Which one's going to have the highest boiling point? The one with the biggest difference, right? If we're looking at boiling point, delta TB equals KB times M times I. Well, I can calculate it all out for aqueous solutions, sure. Or I can just realize that this is a constant, so it's not going to make much difference. And I can look at the number here. Whatever the molality is times the I for that specific system is going to cause the biggest difference. Therefore, it's going to cause the highest boiling point. Glucose, a non-electrolyte. I equals 1. Sodium phosphate breaks up into 4. 3 phosphate ions and 3 sodium ions, 1 phosphate ion. KCN breaks up into 2. 1 potassium ion, 1 cyanide ion. LiClO4 breaks up into 2, Li plus, ClO4 minus. And MgNO3 or magnesium nitrate breaks up into 3, a magnesium 2 plus and 2 nitrates. Some students are going to say, oh, well, this is 4. It is, but don't forget to look at your concentrations here as well. If I take 0.080 times 1, it's going to give me 0.080. Again, you can multiply by your KB value if you really want to. It's 0.512 degrees C per mole. You're welcome to do that, but since it's all the same value, I'm not going to bother with that because I can do the rest of this off the top of my head. 0.060 times 4. That gives me 0. I'm so good at turning on the eraser on these. 0.24. Okay, that's definitely higher. So let's knock that one out. 0.15 times 2, 0.30. Definitely higher. Let's knock that out. 0.10 times 2, 0.20. That's lower. 0.12 times 0.3, or 0.12 times 3, 0.36. This one is going to have the largest difference. Therefore, E will have the largest boiling point. Which one's going to have the lowest boiling point? The one that's going to have the smallest difference because it's boiling point elevation, which one's going to cause the lowest deviation from a pure solution. 0.08, 0.24, 0.3, 0.2, or 0.36. Which one's going to have the highest freezing point? Think about what we mean. We're doing freezing point depression. The bigger the number, the more it deviates from the freezing point. But freezing point goes the opposite direction. Freezing point gets lower and lower. For a higher freezing point, I need the system that has the least amount of deviation. So the smallest number. Lowest freezing point, the one that has the highest deviation. Vapor pressure. What's going to have the highest vapor pressure? The one that's the most volatile, easiest to escape the solution. It's got the lowest deviation. Lowest vapor pressure, highest deviation. Highest osmotic pressure, most concentrated. Lowest osmotic pressure, least concentrated. Think if you can math your way through these. Yes, you can do the math and figure it out. And if you calculate every single one, you're going to find the same results. You can calculate them all out, and I recommend doing that. But I also want you to stop and think about these things and try to picture the molecules themselves. Don't always rely on the math to get you through. Try to see if you can understand that concept and why it's behaving the way it is. That brings us to the Van Hoff factor. Van Hoff factor and ion pairing. Van Hoff factor is this value of I that I keep talking about. And I told you guys that it's 1 if it's a non-electrolyte. Otherwise, it depends on how much this particle breaks apart. It's the number of moles of particles in solution divided by the number of moles of solute actually dissolved. Non-electrolytes, expected and measured, I is equal to 1 for a 0.05 molar solution. Then we've got a bunch of electrolytes listed here. We've got sodium chloride, magnesium sulfate, magnesium chloride, potassium sulfate, iron 3 chloride, and we see that their expected I values are 1, 2, 2, 3, 3, and 4 respectively. But we see that their measured I values are not always matching up to what we expect. You know, sodium chloride, it's 2 versus 2 is it's expected, we see 1.9. Magnesium sulfate, we expect 2, but we get 1.3. Magnesium chloride, we expect 3, we get 2.7. Potassium sulfate, we expect 3, we get 2.6, and iron 3 chloride, we expect 4, we get 3.4. Why? Well, the Van Hoff factor is assuming that these molecules are completely dissociating from one another, meaning they're no longer associating with one another. And the truth is, the more dilute the solution, the more accurate that is. But the more concentrated the solution, the more likely they are to see another ion and still associate with it some. Remember, they are held together by ionic forces. So we call this ion pairing. The chloride here is completely hydrated. The sodium ion is also hydrated, but they're still associating with each other. They're still sensing each other there. What I want you to imagine is imagine yourself back in high school and you're walking through a hallway, and let's pretend you don't know anyone in the room, anyone there. There's just a bunch of people, you don't know who any of them are, so you just kind of go along your day and you walk to your next class. No big deal. You're one particle, you walked along, and you didn't recognize anyone, so you just went to your next class. But then you get out for your next period, you get out in the hallway, and you see one of your friends. Even if there's a lot of people there in between you, and even if you have a quick passing period, chances are you're probably at least going to smile at one of your friends, if not say hi or stop and talk really quick, right? Even though there's a lot of people around, you found your friend. So now you've got that association there. Ions are doing this. The more concentrated a solution is, the more likely these ions are to find each other, the more likely we are to have ion pairing, the less ideal they will behave. Instead of acting as two completely separate particles, some of them will act like separate particles and some of them will not, because they're starting to pair up a little bit. I is almost always less than what we would expect, assuming complete dissociation, because we do have this ion pairing being exhibited. So the Van 't Hoff factor, this is an I, approaches its ideal value as it approaches infinite dilution. So for example, the Van 't Hoff factor for a 0.05 molar sodium chloride solution is 1.9. But if I went for 0.5 molar sodium chloride, I would be less than 1.9. What is it? I don't know. I just know it's going to be even less than that because it's a higher concentrated solution. What about for 0.0050 molar? I know it'll be greater than 1.9, but less than 2. So again, why does that deviate at the higher concentrations? Because it's just more likely to have ion pairing. The more likely it is to find an ion that it's attracted to, the more likely it is to couple up a little bit with it and not act as separate particles. If you know the value of I for one colligative property, you know the same value for all the other colligative properties. Let's work a series of examples just to get you guys more comfortable with this stuff. Calculate the freezing point of a 0.89 molal solution of calcium chloride. I want freezing point. So delta TF equals KF times M times I. KF is 1.86 degrees C per molal. The molality of this solution is 0.89. And I, for calcium chloride, CaCl2, is equal to 3. Plug in everything I know. 1.86 degrees C per molal times 0.89 molal times 3. And the answer here is 4.97. I do have two sig figs here. So the freezing point of water is 0. This is freezing point depression, so I need to subtract. So the temperature of the solution, the freezing point of the solution will be negative 5.0 degrees C. How much ethylene glycol, C2H6O2, in grams must be added to 1 kilogram of water to produce a solution that boils at 105 degrees C? And I do tell you the KB here, but again, you are responsible on memorizing KB and KF values for water specifically. It tells me ethylene glycol, 1 kilogram of water, boiling at 105 degrees C. Ethylene glycol is a non-electrolyte, meaning the I value is equal to 1. I want boiling point, so delta TB equals KB times M times I. And what I'm trying to find is how much ethylene glycol in grams do I actually need to add to cause this boiling point. I know I want 105 degrees C, and I know that water normally boils at 100 degrees C which is a 5 degrees C increase in boiling point. This is equal to my change in temperature of boiling. So 5.0 degrees C, my KB value for water, 0.512 degrees C per molal. I'm trying to solve molal now because I eventually need to figure out the number of grams of ethylene glycol I need, and I is equal to 1. If I solve this for molal, I find this to be 9.77 molal. I'm going to use that to find the number of moles of ethylene glycol I need, and from there I can find the number of grams of ethylene glycol. I've got 9.77 moles of C2H6O2 to 1 kilogram of water, and I'm told I'm actually using 1 kilogram of water. So I know I need 9.77 moles of ethylene glycol. I can add up the molar mass of ethylene glycol, and I find the molar mass to be 62.068 grams per mole. I'm going to use that along with the moles to find out the number of grams I need. I know I need 9.77 moles. I know ethylene glycol is 62.068 grams per 1 mole. Overall, I need 606 grams of ethylene glycol in 1 kilogram of water to produce a solution that's going to boil at 105 degrees C. Number 3, 6.40 grams of an unknown solid are dissolved in 100 grams of benzene C6H6, which is a boiling point of 81.7 degrees C. What is the molar mass of this non-volatile, non-electrolyte solute? It gives me the Kf of benzene, the freezing point of benzene, the Kb of benzene, and the boiling point of benzene. So I've dissolved 6.40 grams of an unknown, that's my solute, 100 grams of benzene, that's my solvent. The solution boils at 81.7 degrees C. I'm told non-volatile, non-electrolyte, and then I'm given Kf, FP, Kb, and BP. I don't really care about Kf, it's just actually erroneous information, but I do care about that Kb. So, because it's a boiling solution, I know delta Pb equals Kb times M times I. I know Kb. I know I, it's a non-electrolyte, so I equals 1. And I know the change in temperature of the boiling point. That should be an equal sign here, not negative. 81.7 degrees C minus 80.1 degrees C. That's this portion. Equals 2.53 degrees C per molal times the molality times 1. I'm going to solve this question for molality. The difference over here, 1.6 degrees C. This brings me down to 2 sig figs. I need to keep decimal places. Equals 2.53 degrees C per molal times molal. And just solve for molal. 1.6 divided by 2.53 gives me 0.632. I'm going to underline that 3 though, because that's where my sig figs are, and the units there are molal. Now I know the molality of my solution. This is also equal to moles of solute to kilogram solvent. I'm told I have 100 grams of benzene. So the same as 0.1000 kilograms of benzene. I can use that information to find the number of moles of my unknown solute. So I've got 0.632 moles of solute to 1 kilogram benzene, because that's my solvent. And in this system, I actually have 0.1000 kilograms of benzene, which gives me 0.0632, keep underlining that 3, just keep track of your sig figs, moles of solute. Now I've got my moles of solute, and I know the original question told me I had 6.4 grams of that unknown solute, so I can figure out the molar mass. 6.40 grams of solute, and by the boiling point, I've determined that we have 0.0632 grams of solute, or moles of solute, I apologize. Gives me 101 grams per mole, but I need my sig figs. I can, 100 grams per mole, still not correct on sig figs because I need 2. So I'm going to write 1.0 times 10 to the second grams per mole. And now my sig figs, now I've got the right answer and my sig figs are finally done. Number 4, find the molar mass of an unknown protein if a solution contains 5.87 milligrams of protein per 10 mils, if a solution containing this has an osmotic pressure of 2.45 torr at 25 degrees C. For this protein, I equals 1. So osmotic pressure, it's a variation of PV equals nRT. It's pi equals MRTI. See, I want to know molar mass. I've got a solution that contains 5.87 milligrams of protein per 10 mils of solution. The pressure is 2.45 torr, and this is at 25 degrees C, and it tells me the protein has an I value of 1. So 2.45 torr. I need that in atmospheres because my R value that I know by heart is in atmospheres. 1 atmosphere per 760 torr. 0.00332 or 322 atmosphere. Now I've got my pressure in atmospheres. So 0.00322 atmospheres equal to my molarity, which I don't know, times my gas constant R, 0.08206 liter atmosphere per mole K. Times 298K. My temperature, 25 degrees C, but in Kelvin, times my I value of 1. Rearrange this equation and solve for your molarity. You should find your molarity to be equal to 1.32 times 10 to the minus 4. And that's moles per liter. Now I've got moles per liter. How does that help me find the molar mass? Well, what are your units on molar mass? Your units are grams per mole. So number of grams of protein divided by your number of moles of protein. We're told in the question that we have 5.87 milligrams per a 10 ml solution. I'm going to write P for protein. I'm going to convert that to grams. I know 1 gram of protein is 1,000 milligrams of protein. Also going to convert the milliliters to liters. I know 1,000 mils is 1 liter. So let's see where we're at right now. I've converted my milligrams of protein. I've converted my mils of solution. I've got grams per liter. But I also have molarity. The molarity tells me 1 liter of solution contains 1.32 times 10 to the minus 4th moles of my protein. That cancels my liters of solution. I've now got grams of protein divided by moles of protein, which is the units of molar mass. So 4.447 grams per mole. Now I just need to look at my sig figs. 3. Looks like I need 3 sig figs. So I can either write this as 4.450 grams per mole. I could write 4.45 times 10 to the third grams per mole. Either one is correct. They both have the correct number of sig figs. So I used the osmotic pressure, figure out the molarity, but then it told me that the solution contained this many milligrams of protein per this many mils of solution, and I just converted that to get to the units I wanted by the end. Now I know the molar mass of that protein. For the last example in this chapter, let's look at this one. What is the freezing point of a 4.0 molar sodium hydroxide aqueous solution with a density of 1.04 grams per mil? The Kf is equal to 1.86 degrees C per mole. So what do we know? We know we have a 4 molar sodium hydroxide solution. We know that the solution has a density of 1.04 grams per mil. I want to find freezing point. So I'm looking for freezing point. If I'm looking for freezing point, I'm using delta TF equals Kf times M times I. What pieces do I know? Kf, I know, is 1.86 degrees C per mole. I know I is equal to 2 because I have sodium hydroxide. So how can I get the molality? What is molality? Molality is equal to the moles of solute over kilogram of solvent. I'm told that I have a 4 molar solution. How do I figure that out? I've got the molarity, I've also got the density, so I can figure this out. But I do have to make an assumption, and this is a safe assumption to make. I'm going to assume that I have 1 liter of solution. That is total solution, that is solute plus solvent. If I assume I have 1 liter of solution, then that means I have 4 moles of sodium hydroxide, which means I have the top of this portion of the equation. Now I just need to figure out the kilograms of solvent. Well, if I have 1 liter, and I know the density, 1 liter of solution, I'm going to convert that to milliliters. Why? Because my density is reported in grams per mil. Multiply that by my density, 1.04 grams of solution per 1 liter of solution, 1 milliliter of solution. My mils have canceled, my liters have canceled. This is going to give me my grams of my solution. When I calculate this out, I get grams of solution equal to 1,040 grams of total solution. But that's not completely helpful because I need kilograms of solvent, not solution. I do, however, know that I have 4 moles of sodium hydroxide. If I know the moles of sodium hydroxide, I know how much that weighs. I just need to convert to grams. Sodium hydroxide has a molar mass of 40 grams per mole. Four times 40 is equal to 160. Sig figs are here. 160 grams of sodium hydroxide. do pay attention to where your sig figs are, because with addition and subtraction, this can get messy. I now know that my solute weighs 160 grams. My solution weighs 1040. So my solvent is equal to 1040 grams of solution minus 160 grams of solute. This answer gives me 880 grams of solvent. My sig figs are here at the tens place because of the 160 grams of solute, where my sig figs are. I now know my grams of solvent, and this is equal to 0.88 kilograms of solvent. 0.88 kilograms of solvent. 4 divided by 0.88 gives me 4.55 mol for the solution. So this part here is going to plug in right here. Please pause if you need to write stuff down, because I need to move some of this stuff around so I can actually fit the rest. I didn't plan the slide out well when I started writing, but I don't want to delete things on you either. Now that I have my molality, I can go ahead and calculate the change in freezing point. So delta TF is equal 1.86 degrees C per mol times 4.55 mol times 2. Calculate this out, and my sig figs are here. So 4.55, I'm just not rounding yet, gives me 16.9 degrees C. 2 sig figs is 17 degrees C. But remember, this is freezing point depression, so my actual freezing point here will be negative 17 degrees C. And that's kind of pulling in a lot of the concepts we've learned in this chapter with how to calculate concentrations of different solutions, as well as determining colligative properties.